So this is still in Chapter 9. This is still under the analytical geometry bubble of Chapter 9. It'll be like the concepts discussed in Chapter 9. You will use these in calculus. If you don't get them in Calc 1, you'll get to them in Calc 2. But you will see them. If you're in physics right now, you'll also see there's a little bit of overlap between this and physics. Once we start getting to the application, the word problems. But we will do projectile motion slightly different than physics does projectile motion. So if you're in physics, it's similar, but there's like a little tweak to the formula that we use versus the physics model. So the first page is a little information about parametric equations. And it tells you to consider the path followed by an object that is propelled in the air at an angle of 45 degrees. This equation, y equals negative x squared over 72 plus x, is called a parabolic path. So we will be creating our own equations using the angles, sine, cosine, and tangent. Well, actually, sine and cosine are going to come back into your life in this little section that we look at. But we will be talking about velocity, the speed of an object, the angle the object occurs at, and we will go through how to get an algebraic equation with that information. So the equation up here we will be creating. But generally, when you have an equation with variables x and y, it says it makes a parabolic path, which we just talked about parabolas in that geometric form. So if this is a parabolic path, it's starting somewhere. It has a negative in front, so it might look something like this. So it's a parabola that goes down. No longer our parabolas go left and right, so we're back up to the up and down part. So we're in that y equals form. But it says the equation doesn't tell us the whole story of the graph, because graphs have stories. So, I mean, who knew a graph had a story? It says this tells you where the object has been, but it doesn't tell you when the object was at a given point. So the where part, it tells us the horizontal distance. So this part here is our x, so it tells us how far horizontally the ball has traveled, or whatever object it is. It also tells us how high it's traveled to get to this point, because that point has an x and a y value. So that's the location, but it doesn't say how long it's taken to get there. So if I throw a ball and I want to find where it is at the maximum, I can get the maximum, but how long does it take to get to the maximum? And you can't tell that with having x and y, because x is horizontal, y is vertical. There is no time taken into account. So we're going to throw that extra piece of information into the problem by inserting a third variable, which is called a parameter. So it gives us some specifications as to about how long does it take to get to that specific location. Is it 3 seconds? Is it 5 seconds? Is it 10 seconds? Especially if I want to find when the ball hits the ground or when the ball is at its max. So our third variable, the parameter, in most cases is t, because it's going to represent time, so that we can find when the object is at a certain horizontal distance and height corresponding with an xy point. We will also see that variable change into an angle. Sine and cosine are coming back. We'll kind of spiral this back in. And of course, that will be there when we are talking about sine and cosine. So the typical angles that we would use, think of like your angle of 0, the angle of pi over 2, the angle of pi, the angle of 3 pi over 2, those quadrant angles. But the variable could be time, or it could be an angle in retrospect, like to the location of the unit circle. So still x and y, because every unit circle has an x and y point, but the angle correlated with that. So it says it is possible to write both equations x and y as functions of t to obtain parametric equations, and it's pluralized. So we actually will now have 2 equations for every graph that we look at. You'll have an equation for x, and that equation will be defined with the variable t. So I still have just an x and a y, but that t is now kind of in the equation. So we have this 24 square root 2 times t, and then next to it we have a variable, or an equation for y, negative 16t squared plus 24 root 2 times t. Again, these equations we will find by using sine and cosine and the angle, the velocity that the object is occurring at. But those 2 equations are created from the original equation that's up there. So we'll talk about how to go from a y equals with an x equation to an x and y individually. So parametric equations, you'll always have one for x and one for y, so that I can create that ordered pair. So again, kind of following along, using these equations, we can determine where the object is at any time for t. So at 2 seconds, I can know the horizontal distance and the vertical distance just by plugging numbers in for t. It says the resulting path is called a plane curve. So the path that the object takes with respect to time is not just a typical xy graph. So it gets a special name that we will graph still in the coordinate, the xy axis, but it will be a curve and it's called a plane curve. We plot points in a specific order. So as time increases, we will be plotting points from left to right. So if I have -5 seconds versus +5 seconds, yes, I know time can't be negative, but we'll still be kind of thinking about a negative value versus a positive value. But we will be plotting them in a direction based off of time increasing, and that direction is called the orientation of the curve, which is pretty much the direction that the graph will be going. So you'll see little directional arrows on your graph, so that I know that it starts at the left and moves to the right, or it could start at the right and move to the left. It doesn't always have to start from left to right. And it's just based off of like how the graph or how the curve is reacting to time. So not every graph, when we draw this parametric set of equations, will move from left to right. So we're going to see if we can try and look at our first set of parametric equations and graph them so you can kind of get an idea of what it looks like. We will also graph it using the calculator. So we have the first one here, we have an x and a y. So you'll have 2 equations now, one defined as x with a t, one defined as a y with a t. So it's not like I have 3 variables in one equation. So we're not there yet. That's multivariable calculus. That's dealing with vectors, x, y, and z in one equation. So kind of, we're just looking at the x and the y right now. It tells us that our t, our time, goes from -2 to 3 seconds. So that's the restrictions that we're given. So we're going to graph this from -2 to +3 seconds. The easiest thing to do is for you to make a little t-chart. But our t-chart now has a t literally in it and the x and the y. So make yourself a little t-chart. I'm going to make mine going horizontally because I feel like you have more space horizontally than vertically. So we have t, and then we'll have x and y. So there's my 3 variables. We need to plot a point for every amount of time that is accounted for in our restrictions. So our restrictions go from -2 to +3. So every second we're going to be plotting a point, starting with -2 and going up to +3. So take your time values, plug them into the parametric equations. Get corresponding x and y values. So fill out the table of values here, and then we'll see if we can graph this, trying to figure out what's going on with the graph. So again, you're taking t, plugging in for the t in the x equation, plugging in for the t in the y equation. So one t value gives you the x and the y ordered pair. Sean, what did you get when you plugged in a -2?
For which one?
X and y.
I got 0 and -3.
How about when you plugged in a -1?
-3 and -1.
Plugging in 0,
-4 and 0.
a 1,
-3 and 1.
positive 1/2 or negative 1/2?
Positive.
And then when you plug in a 2?
0 and 1.
And then a 3.
5 and 3.
Any questions? All right, so we're going to graph these. We're not graphing t, we're still graphing x and y. So we're using time to create x and y values. So make yourself a little xy axis, just like we did with the conics. Just kind of doing a little bit of freehand graphing here. And then plot the points. So you're starting with the first ordered pair. So you're graphing 0, -1. You're not graphing the -2 value for time. We use time to create x and y values. And then you connect them in the order that you plotted them. So the first one we graphed was at 0, -2. I'm sorry, 0, -1. We moved to the left when it hit the point -4, 0. And then it started to move to the right. And it's going to stop here. So then you have to, like, this graph is called my plane curve. It's the curve that was created from using the parametric T. So dealing with time. The last thing we need to do is graph the orientation, which shows the movement of the graph, because I physically can't watch all of you graph it. So we're going to draw little arrows to show the direction that the curve moves. It started here, and then the little directional arrows show how the actual movement occurred. So think when you graph in your calculator, it always starts like graphing a y equals problem. It always starts on the left and it moves to the right when it's graphing. So this is going to do the same thing when you graph it in the calculator. It's going to start underneath, it'll move left and then turn right. But I physically need to see that movement now because it isn't always left to right. Every other graph in y equals is just left to right, but now the graphs will change. So that is called a plane curve. That's the name of a parametric set of equations that creates the graph. And it has the orientation, the direction that it's moving. So essentially, my y or my x-axis is like the ground. So at -2 seconds, the ball or the object would be under the ground. This time is negative. Once I hit 0 seconds, now my path is above ground. So like think of the x-axis now as your ground level. Everything above it is once it starts appearing above the ground. Questions? So in your calculator, you want to take that thing out. We're going to see if we can change this to parametric equation form. If you're using the calculator for something else, do you guys graph anything in the calculator in like chem or physics or bio? You don't use the graphing capabilities. You'll have to switch back and forth. If you're graphing in some, like if you're graphing to graph y equals mx plus b or something like that, you'll have to go back to the regular form. So we are going to go to mode, which we used before in trig. Remember, we have that radian versus degree mode. So keep it in radian for now. If you're asked to change it to degree, change it to degree. But then going underneath the fourth one down, ours is in function form right now. That's like having the y and the x. If you go to parametric form, the PAR, that puts it in the form that we will be using. Next to it is polar coordinate graphing, so that'll graph everything with respect to polar values dealing with sine and cosine, and then we have sequential graphing. So there are actually 4 different functions that the calculator does. So we're going to go to this parametric form. So make sure it is now darkened. And then you're going to go to your y equals, and you should see you now have an x with respect to t and a y with respect to t. Because I have 2 equations. We have an x and a y. So we don't just have y equals anymore. So in that first one, if you can place the equation you were given, so that's t squared minus 4. So the variable that you're going to see appear is t. Because now like in that little area, usually it's x when it's a function. T would be parametrics. Polar coordinates uses the angle theta. Sequences use n. So depending on what function form you're in, will depend on the variable that you're using. So that variable changes based off the form of the function. Was it t squared?
Yes.
Yes, thanks. T squared. and then minus 4. And then the second one I think was t over 2.
Yes.
Yeah. All right. So before you hit graph, we're going to kind of keep changing it. So if you go to your window, the window changes as well. So you see the t, the time max and the min, and then the t step is how quickly it graphs something. So the smaller the t step, the more points that it actually plots. So see if you can just change those pieces of information according to what is given underneath. And it just goes vertically. So change your time. It's 0, -2 to 3 because that's how we graphed it. The t step we have as 0.1. My x values go from -5 to 5, as well as the y values. So then when you hit graph, you should see the identical graph, and it graphs it really fast. Like really fast, and that's because of that t step value. So
If you do trace, you have to hit the right to go left.
Yes, it's kind of weird.
Bruh.
Questions so far? Grant,
I'm sorry, I missed how you got the t-step value.
the t step value. Wait.
Like, why'd you put 0.1?
Oh, that number will change. It'll just depend on what we're working on. At this point, it doesn't matter.
Okay.
So, the smaller it is, the more points it plots. So it's plotting more. If I had a larger number, it would like skip, and it wouldn't plot every point. So it like skip from here to here. You'll have an activity tomorrow that you'll be like changing that value just to see how that number changes and how it affects the graph.
Right, so if we like change it to 1, we get all blocky and stuff.
Yeah. I mean, you guys could. Yeah, you'll be kind of playing around with that t-step value and seeing what happens. It graphs it slower, it graphs it faster, depending on what that number is. Questions? All right, so if you flip the page, we're gonna kind of graph another one by hand. We'll try and graph it with the calculator as well, just to see how it changes with the calculator. So graph the curve, and then it says, what do you notice? So we have this set of parametric equations for x and y. 4t squared minus 4, y is just equal to t. But then the time goes from -1 to 3 halves. So the time has changed as well. So Jesse, you probably want to count by halves. Yeah, so if it goes up to 3 halves, now we're counting by half seconds instead of whole seconds when we're looking at our time. So starting at -1, -1/2, 0, and so on. Jesse, what do you notice about those points?
They're like, wait, is this thing? Yeah. It's on a different page, so I don't know.
It is on a different page, huh?
Jacob got
One is 0, 1, 3 halves was 5 and 3 halves. So these 5 ordered pairs, 6 ordered pairs, are actually the same ordered pairs that we just had for the previous graph. Making yourself a little graph. And it's okay if you didn't notice it yet. I know it's on a different page, so you have to flip back to kind of realize it. But plotting these points, our first one is at 0, -1. And then at -3, we're down at a half. At -4, it's at 0. -3, +1/2. 0, +1. And then 5 and 5/2. So it creates the same exact graph as the one we already looked at. But the numbers are different. Because we have a 4t minus 4, and you have a y equals t. What has changed? Nothing, technically, in the graph, but what has changed with our parameter? So look at the parameter. The parameter is the third variable. How has the third variable changed? Jacob?
It was cut in half.
Yeah, it was cut in half. So our previous problem, the first one we graphed, was from -2 to 3 seconds. That amount of time was literally cut in half. So we have half the amount of time. So that kind of like creates the same graph because we've changed the other values instead of by cutting them in half, we've changed them as well. So kind of just looking at those, here we go. So we now have 4t squared, so that number in front has kind of been doubled, and it's just t instead of t divided by 2. So we doubled the equations, but we cut the graph, the time in half. So underneath it talks about parametric equations. There you go. So it says, comparing t-values, this graph is technically traced more rapidly, so over a shorter amount of time. Different parametric equations can be used to represent various speeds at which objects along a path travel. Parametric equations defining a curve are not unique. So that means that in a regular algebraic function, y equals 3x plus 1 only gives you one graph. It'll just give you a slope of 3, a y-intercept of 1. A regular function is a unique equation. Parametric equations are not unique, so I can have multiple equations representing the same exact graph. The part that's going to change would be the time, so they're not special, no. So a line y equals mx plus b, that one equation only gives me 3x plus 1. I can't tweak that at all. However, with parametric equations, if I tweak these numbers and the time, I can get this graph an infinite amount of times. I can have an infinite amount of equations, but the same graph can be graphed from those various different equations. So the picture's going to look the same, but the equations that we use to get there and the amount of time might be different. Questions? So we are going to look at another problem, but we're going to try and get the point plotting out of the problem. So it says for the last example, which really the last two, we used point plotting. We created a t-chart. We picked x and y value, or t values, and we created x and y values. This can be tedious. It can take a little bit more time. And sometimes going back to the regular rectangular equation. The rectangular equation is the one that has y and x. So y equals 3x plus 1 is a rectangular equation. A parametric equation would be the set of equations for x and y. So when it says find a set of parametric equations, you always need two. When it says get a rectangular equation, you're going back to the form that you've known, having the x and the y graphing together. It says we do this by eliminating the parameter. So we're going to take these two parametric equations, we're going to eliminate the parameter, which means we're eliminating t. And we're going to go back to the form that we have pretty much graphed in all year, all last year, probably all of Algebra 1, which is when you usually have a y and an x, because that's pretty relatable to us. Usually it's things that we can graph pretty quickly. So looking at the original problem, so this is the same problem that we started with. We have x equals t squared minus 4, y is equal to t over 2. The directions say eliminate the parameter, which means eliminate t. So our goal is to get rid of t. To find a rectangular equation, one equation that has the x and y back in it. How do you think you do that? Alina?
So for t, one equation and plug it in the other.
Yeah, so we're going to use substitution. So if I have three variables, if we can get one of them by itself, we can always substitute that back in the other. Which one do you think is easiest?
Y equals T over 2.
Yeah, so probably that y equals t over 2, Elena, because t would be equal to 2y. So to eliminate t, you're going to take one of those equations, and it doesn't matter which one, pick one. Get the t by itself, because that's what we're trying to get rid of. So we want to get rid of t, so if I solve one of them for t, then we can kind of get rid of that value. Take whatever it's equal to, use substitution, and go back into your other equation. So now in this other equation, we have x equals t squared, so t is 2y. It's squared, and then we have minus 4. And what do you have to do with it? Right, what else would you have to do with it?
What do you have to, like, do the exponent from the 2 and the y?
Yeah, so the exponent applies to the 2 and the y, so that becomes 4y squared. What else, Greg?
I don't know.
What else would you typically do with an equation? Solve for y. Yeah, so we're going to try and graph this. We could try and solve for y. So take the 4 to the other side. So add 4. Divide by 4. So y squared equals x plus 4 divided by 4. And finally, square root it. So can that be simplified if we're taking the square root? Abby?
The denominator.
Yeah, the denominator can. So we have the square root of x plus 4. The denominator can just become a 2. What else is my equation missing? Emily?
Plus or minus.
Why?
Because we're adding in the square root. Since it's
Yeah, so it was y squared, which makes that horizontal parabola, which we just talked about with the conics. So if we're solving for y, getting y by itself, then we have that plus or minus form.
I got it in the form like that we did with the conics.
That's fine, yep. So if you want to have it in the conic form, you can keep it in the conic form. So if we're graphing this, first off, is there a restriction on x because we have a square root in the numerator? Sean?
X can't be less than negative 4.
Yeah, so it can't be less than negative 4. It can equal it, so we'll say x has to be greater than or equal to negative 4. So that would be a restriction because there's a square root. So I can't just pick any random x. Make yourself a little mental t-chart. Or Elena said she kept it into the conic form that we've been graphing, and then you can graph it like that as well. We're going to see if we can just do a quick little graph here of this function. So we could plug in a negative 4. You're allowed to plug in a negative 4. So if I plug in a negative 4, I have the square root of 0. So at negative 4, we have a 0. What would be another good x value that we could plug in? So if you want to make a little t-chart, you can. I'm just doing a mental. So I plugged in a negative 4, I got out a 0. What other number could we plug in? Ben?
Yeah.
A 0. If you plug in a 0, Ben, what number do you get out?
1.
A 1? Another good number to plug in, Abby.
Negative 3.
Negative 3. If we plug in a negative 3, Abby, you get out a? 1/2. So negative 3, we have a 1/2. What else goes with that 1/2? A negative 1/2. Also with the 1 because it's plus or minus. And then we could plug in one more number. What number? Another good number to plug in. Emily?
5.
A 5. Because when you plug in a 5, Emily, you get
1 or 3 halves.
3 halves, yeah. And again, that plus or minus, because it does say plus or minus there. 4, 5, up 3 halves, down 3 halves. And if I connect them, I end up with a parabola. The identical parabola that we just graphed, except the other one started at 0, -1. But it's the same exact graph. It's now going horizontally because the y was squared, so it's the horizontal form instead of the x being squared. Questions? Emma?
Does that one have a direction?
Not because it is back into rectangular form. When you're graphing it on the calculator, it'll always graph from the left to the right. Every rectangular graphs from the left to the right, so we don't have to include a direction. So it would start at the -4, and it would graph the -3, then it would graph the 0 and the 5, because x starts on the left and just moves to the right. Other questions? So we are going to see if we can do another problem on the next page. Same example, same type of problem. So it's going to ask you to eliminate the parameter. It does ask to graph as well. So find the rectangular equation of the curve whose parametric equations are as follows. Graph this curve, and then it does say indicate the orientation or the direction of the curve. So in this one, we'll see if we can kind of show the way that it would be graphed. Which one would be easier to eliminate? Sean?
Y equals t plus
So he said you could go to the y equals t plus 2 and make it
2. T equals y minus 2.
so that would be one way. What if you wanted to get the t by itself in the x form? Morgan? Yeah, you could say t equals x squared. I actually think both of them are pretty straightforward. Sometimes it's nice to try and use the x variable because then you're already in y equals form and then you're saving yourself a couple less steps to get y by itself. Totally personal preference if one of them can be easily solved. So if we use the t equals x squared that Morgan gave us, you're taking x squared, you're plugging it into y. Sean, not that she's better than you. Don't want you to think that.
I'd never think.
Okay. So if you plug that in, we now have x squared plus 2. You could do the exact same thing by plugging y minus 2 in for t, squaring both sides, and then solving for y. You'd still get x squared plus 2. The next thing you have to think about is their restriction on x. So looking at the original equations, not my new equation because my new equation says x squared, but going back to the original, are there certain values that x can't be? Emma, why can't it be negative? Yeah, so we have the square root of t, and when you take a square root of any number, it's going to be positive unless the plus or minus is in front of it. So x is always going to be positive. It's allowed to be 0 because the square root of 0 is 0. So that's because there's a square root with the t. X is only going to be a positive answer. So you have to make sure that you're kind of including that restriction. So we're asked to graph it, and then we're going to indicate the orientation, so the direction that it moves. We're going to get at that orientation by kind of thinking of the original problem instead of the new one. So if this is x squared plus 2, Abby, what happens with x squared plus 2?
It's a parabola.
A parabola, and this parabola starts at?
It would start at 0, 2.
Yeah, it starts at 0, 2. So here's my parabola starting at 0, 2. We only need the positive x side. So x must be greater than or equal to 0. So if I plug a 1 in, I would move up 1. Make my graph go a little higher. If I plug a 2 in, I would have to move up 4. 1, 2, 3, 4. So Emma asked earlier about the orientation, and we're going to see if we can do the orientation of the curve. Except when you do the orientation of the curve, you have to refer to the parametric equations. So if I pick a time of 0, so when time is 0 and t is 0, I have the square root of 0 and I have the 0 plus 2. So my first point is at 0, 2. I just need to plug in one other amount for time to get the direction. Because once you have it from one point to the next, you know the direction of the curve. So if I plug in a 1, the square root of 1 is 1. My next point is 3. So that means the direction of this curve is moving how a traditional curve would move, or a traditional graph would move, from the left to the right. So plugging in two time values gets you then the direction of the curve. Questions? I have time. Yeah. I want to start number 3 with you, or letter C, not number 3. Letter C with you. So, see if we can have time to just start this guy. Everybody's friend. Sine and cosine. So, what do you think the parameter is in this question? T was in the others, the 4 that we looked at. T was in it. What's the parameter in this, Ben?
Theta.
Theta. And what's attached with theta, Ben?
The cosine.
The cosine, or the sine. So we're actually going to solve for both of those. Ben, if you get cosine by itself, what would it be?
It would be cosine theta is x divided by
And if you got sine by itself, Ben, it would be?
y divided by 4.
There's no way, well, yes, there's a way. We could use inverse functions to actually solve for the angle. But what equation do you know contains sine and cosine together in the same equation? Tangent, what else?
Cotangent.
Ooh, that one.
You'll have to use that one for, I think, 2 of the problems. So make sure you jot that down to remind yourself. Anybody interested in doing 17, 19, 23?
Where are you coming? On this extra credit.
Yeah, extra credit.
Extra credit.
You know, the,
So Abby, Alyssa, Morgan, Mason, Jacob, Schultz, Hannah, Elena, Alice. No takers? Have an awesome day.